Alright everybody, I'm going to walk you through electron configuration and energy diagrams. This, along with the other resources that I've put on the classroom, should be helpful to you. First thing we need to do is split the periodic table up into blocks. The S block is the alkaline earth metals and helium. The D block is the transition metal middle area. P block are main groups 5 through 10. And then, for your information, lanthanide and actinide series are the F block, but we will not be talking about those because things get really weird, and the Ohio State standards say that we do not have to go past barium. So barium will be the last one you'll have to be responsible for knowing how to do for electron configuration, and we will not be talking about exceptions to the Aufbau principle, so we're going to keep it really basic. The first thing that I'll tell you, other than just the blocks, is that the N number, which is the principal energy level, is 1, 2, 3, 4, 5, 6. We will not be going past 6 because that's where barium is. And for the electron configuration, there is the energy level or shell, which you just count down your rows. And then we have subshells, S, P, D, and F. And then within those subshells, there are a different number of orbitals. And each orbital can only contain 2 electrons. So as we are working through here, looking at the periodic table, you know that the atomic number for hydrogen is 1, helium it is 2, so on and so forth. That tells you how many protons there are, and as long as it is not an ion, that will tell you how many electrons there are also. So if you are looking at any element, yttrium, there are 39 electrons, and so once you are done, you can count up all of your superscripts, and then you'll be able to figure out if you did it correctly or not. It's kind of a self-check. So, this is going to seem really weird at first, and you might be frustrated, but it's not too difficult once you get down the basic concept. Okay, so for electron configuration, looking at hydrogen, look at what energy level you're in. 1. What subshell are you in? S. And then how many over have you gone? Just 1. So for hydrogen, the electron configuration is 1s1. You are done. Next up, helium. Energy level, we are still at the first energy level. We are still in the S block, and you are going over 1, 2, 1s2. So helium is just 1s2. Next up, lithium. You might want to just skip straight to where you start, but for electron configuration, you have to account for every electron in the atom, and so you have to work your way all the way back through, starting from the beginning. So, if lithium is in the second principal energy level, you have to account for the first energy level as well. So, you will start with 1s2, and then 2s1. And it will build upon itself in this fashion as you go along. So looking at oxygen. Oxygen is over here, still in the second energy level, so we have to account for all electrons. 1s2 takes us to helium. 2s2 gets us through beryllium. Now we're over here, 2p, 1, 2, 3, 4. So for oxygen, it's 1s2, 2s2, 2p4. Next we go to sodium, so we have to account for everything leading up to this third energy level. So we're going to go 1s2, 2s2, 2p6 gets us to neon, and then we can go 3s1. So for sodium, 1s2, 2s2, 2p6, 3s1. Chlorine, we're still in the third energy level, so we'll go 1s2, 2s2, 2p6, 3s2. That gets us 2 magnesium. Then we hop over here, and then we're at 3s, 1, 2, 3, 4, 5. 3p5, sorry. Next up, calcium. So we have to account for everything in the first 3 energy levels. 1s2, 2s2, 2p6, 3s2, 3p6 gets us 2 argon, and then we have to go down to 4s2. So everything is pretty straightforward until you get to the D block. So if we are going to do manganese, we need to go through up to calcium, so we can copy off of our work. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then the weird thing about the D block is that the energy level will be 1 less than what you think it should be. So even though all of the S block and the P block will be in the 4th energy level, the first row of D block elements will be in the 3rd energy level. So we will go 3D, 1, 2, 3, 4, 5. That's probably the most confusing thing about the electron configuration, is remembering that the first row of the D block is at the 3rd energy level, second is the 4th, then you don't have to worry about anything beyond that because we are stopping at barium. This is kind of labor intensive. There's a lot of repetition, and so there is a way of abbreviating this using a noble gas configuration. So you all remember these are the noble gases, and so if we did not want to write all of that out for manganese to save time, what we would do is find manganese, go back to the nearest noble gas, which is argon, put that symbol in brackets, and then continue from argon. So from argon we would go 4s2, 3d5. So you can see that is a lot shorter than all of that. This is the noble gas abbreviation. You can use noble gas abbreviation for any element as long as it is not abbreviating itself. So if we wanted to do argon, you can't just put argon in brackets and call it a day. Not cool. You would have to go back to neon and then go through your 3s2, 3p6. That is it for electron configuration. Next up will be the energy diagrams. These are very easy. You will have a paper that looks like this with all the boxes. You can see once you're at 4s, the 3D energy level is kind of intermediate between the 4s and the 4p. That is the explanation for why you go 3D for your first row of transition metals. I'm not going to go into greater detail because that's beyond the scope of this course, but if you are curious, that is the explanation I'll give you. So, for the energy diagrams, let's just say we were going to do manganese again. What you will do is take your electrons, in which case we would have 25 of them, and you will populate these orbitals. So the S subshell only has 1 orbital. It can only fit 2 electrons. Electrons will have an up spin or a down spin. So far, super easy. Up and down, 1s, 2, 2s, 2. And then once you get to subshells that have more than one orbital, you'll have to maximize the number of electrons with the same spin. So they will all be upspin first. And then once you double it up, you go down spins. And there is a document explaining the Pauli exclusion principle, Hund's rule, all of that. And so as you're going through putting your 25 electrons in, you can go up, down, up, down, up, 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 down, 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 up, down, up, 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 down, 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 until you get your 25. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 20, and then 1, 2, 3, 4, 5. So you'll want to maximize electrons with the same direction of spin, up or down. I like to go up, and you'll proceed in that fashion. And so that would be your energy diagram for manganese. If we were going to go to the next element, iron, then we'd put a down spin there. So you have to put one electron in each of the orbitals before you double it up, like in this first orbital. The document that I have included on Classroom explains that a little bit more. Didn't want to make this video super long, and so email me if you have any questions, and enjoy your extended break.